Welcome to this tutorial from the spec to the exam. Today's topic is catalyst. We're going to revisit very briefly the basics and then dive deep into the transition metal equations that you need to know. No matter which exam board you are doing, you have to be able to explain the role of the catalyst by writing a nice and clear definition. Let's look at a specification. Specifically, we're looking at the OCR specification, but this is for all of you. This is actually AS content where we explain the role of the catalyst. So what is a catalyst? And let's use the same words that the spec uses. A catalyst increases the rate of reaction without being used up by providing with a different route with lower activation energy or by lowering the activation energy. So what is a catalyst? A catalyst is a substance that increases the rate of a chemical reaction without being used up by providing an alternative pathway with lower activation energy. There are some things that you have learned across the spec that it might not be super obvious, but you need to remember that a catalyst does not affect the enthalpy change of a reaction, nor it altered the position of equilibrium. This is because it only influences the kinetic of the process. The reaction proceeds faster under the same condition. It lowers the activation energy of both the forward and the backward reaction if we're talking about a reaction in equilibrium. In a diagram that looks like this, where the activation energy, which remember in an enthalpy diagram, it's always from the reactant to the top of the curve, this being the activation energy of the uncatalyzed reaction, the activation energy of the catalyzed reaction would be lower. But remember that for the backward reaction, the activation energy would also be lower. So the catalyst speeds up the forward but also the backward reaction. And that's why it does not change the position of equilibrium. There can be two types of catalyst, homogeneous and heterogeneous. An homogeneous catalyst is in the same physical state as the reactant, usually aqueous or gaseous, and we've seen many in organic chemistry. So remember that this typically involves the catalyst forming an intermediate species with the reactant, and the intermediate, it then decomposes to regenerate the catalyst. Remember, is in the same physical state. An heterogeneous catalyst is in a different physical state from the reactant, usually a solid with gases or liquid reacting on its surface. And the process is slightly different. It involves several essential steps: adsorption, weakening of bonds, reaction, and desorption. Adsorption of the reactant molecules onto the catalytic surface is basically forming an intermolecular force, not absorption, where the reactant would be actually taken inside. No. This adsorption causes weakening of the bonds, which causes reaction on the catalytic surface and causes desorption of the product molecules, leaving the catalyst available for use. Now, the catalyst surface, remember, contains active sites that are very important for these reactions. Do you remember any example from organic chemistry? Hydrogenation and catalytic converter. Remember the nickel catalyst in hydrogenation of alkenes to alkanes. And catalytic converter. Let's see an exam question with catalytic converters. A catalytic converter decreases the emissions of gases such as carbon monoxide and nitrogen monoxide from an internal combustion engine. Describe the stages in a catalytic converter that result in this increase. No equations required. So for these 3 marks questions, we need to state 3 key points, which are the 3 key stages. Do you want to try? Pause the video and try yourself before I give you the answer. Mark number 1, it's for the adsorption. We can go more specific, of course, in this example because we have adsorption of what? Carbon monoxide and nitrogen monoxide and or molecules where on the catalytic surface, or you could also say on the active site. Second mark, what is the consequence of this adsorption? Is the weakening of the bonds. And the same mark would be worth if you say the chemical reaction between carbon monoxide and nitrogen oxide. If you also say breaking the bonds, it's fine. And remember, the bonds that is weakening is not the intermolecular forces between the molecules, but it's is the covalent bond between the carbon monoxide and nitrogen oxide in this specific example. Because this is the bond that you want to break, not the intermolecular force. And the third mark is for the desorption of the products. You can say desorption, you could say the product leave the catalytic surface, but make sure you use the keyword desorption. No equation is required, but you might want to mention the products, which is carbon dioxide and nitrogen gas as a product, again from where? From the catalytic surface. And here are your 3 beautiful marks for this question. Let's move on into the next type of catalyst. Homogeneous catalysts, they form an intermediate. And here on top of your head, what is an example of homogeneous catalyst that you have seen before? Maybe in organic chemistry. Acid H2SO4 is a very common catalyst that we see in organic chemistry. For example, the conversion from or the reaction between carboxylic acids and alcohols to form esters. Remember, here the H plus is a homogeneous catalyst. And like the reactant and product, it's in its aqueous phase. One very important concept about heterogeneous catalysts is that they may lose its effectiveness. In fact, remember that these catalysts, they can become poisoned. And here we can see many exam questions where they ask how might heterogeneous catalyst lose its effectiveness, or how could you improve the effectiveness of an heterogeneous catalyst. So how do we prevent this poisoning? By removing the impurities or purifying the reactants. And by the way, why do they become poisoned? Because impurities, they bind, so they absorb actually this time, absorb more strongly on the surface, so that there are less active sites available for the actual reaction. So remember, how can we improve decrease the chances of poisoning or increase the effectiveness? Purification. And here I'm saying bye to OCR students because that's it for you. But AQA and EdXL, you have to keep up with me. We still have a lot to go in this topic. Now we need to make the link between catalyst and transition metals. In fact, this is an important explanation in the topic of transition metals. Now, we need to explain why some transition metals act as catalysts and why some don't. So transition metals, they act as a catalyst because they have a variable oxidation state, which means that if you have a question of, for example, why does zinc not react as a catalyst? Well, because it only has one oxidation state, zinc 2+. This is just an example, but we need to remember the importance of variable oxidation state in catalysts because we need to know how to write 3 specific equations which explain one heterogeneous catalyst, one homogeneous catalyst, and the concept of autocatalysis. And this is for both of you, AQA and at Excel. Let's go into the equations. The contact process is an example of heterogeneous catalysis because it works by solid sulfur reacts with oxygen to form sulfur dioxide in this first step of the reaction. The second step is an equilibrium reaction where sulfur dioxide reacts with oxygen to form, remember it's an equilibrium reaction, to form sulfur trioxide. Now, this reaction and this second step is catalyzed by vanadium, specifically V2O5, so vanadium oxide, vanadium in the oxidation number of +5. Now, the vanadium catalyzes. What it does, it converts sulfur dioxide into sulfur trioxide, and itself it's reduced. Now, what is important is that you have very clear the catalyst involved. So we have a V2O5, which itself changes to V2O4, and then of course changes back to V2O5. So as a little side note, I think it's useful to know the difference in oxidation states. So we go from +5 to +4, and then of course back to +5. Now, we know that, and here you can figure it out in different ways. One is that you write the half equation for the reaction, for the change between sulfur dioxide and sulfur trioxide, and instead of the electrons, you would write the catalyst. Or you can just think about if the sulfur dioxide changes to sulfur trioxide, as we can see, it gains oxygen, itself is oxidized, which means that the vanadium must be the opposite, it must be reduced. In fact, this is how the steps goes. SO2 plus V2O5, and remember, this is a solid, this is a gas, remember, heterogeneous catalyst, to form a V2O4, also a solid, and the sulfur trioxide. Notice the changes in oxygen. And then, of course, the second step is the regeneration of the catalyst. But if we know that in our overall equation we have oxygen, well, where is oxygen in these steps? This is what it's reacting with the catalyst to reform it, to reform V2O5. Yeah? We can balance it with two of those or with half of the oxygen. And now let's go with the example you must know for homogeneous catalyst. The reaction between iodide and the peroxodisulfate ions, what a mouthful that is, don't worry, you don't need to know the name, it's catalyzed by iron. And of course, iron, it's a catalyst. Why? It's a transition metal, and it's used as catalyst because it has this ability to form two different ions, Fe3 plus and Fe2 plus, which means that it can act as an oxidizing and reducing agent. Now, you can have very interesting questions like, why would this reaction need a catalyst in the first place? Now, this reaction is quite slow. Why? Because both iodine and this peroxy blah blah is negatively charged. So they are very unlikely to make successful collisions with one another, which means that iron is what helps with the transfer of electrons. And this is how it goes. In the first step, we have this molecule reacting with the ion 2 plus to form SO4 2 minus. And guess what happens in terms of transfer of electrons? Now here, feel free to analyze this, the change of sulfur in terms of oxidation number, in terms of half equation, because you will notice the transfer of electrons. Now, Fe2 plus goes to Fe3 plus. If we balance this equation, it goes like this. Now, the ion 3 plus, it has to reform the ion 2 plus, so it will oxidize the iodide to form I2 and reform the ion. So the ion produced can then go on to reduce more of the peroxide sulfate, so it fulfills this role as catalyst. Remember, this lowers the activation energy of this reaction, which, why does it have such a high activation energy? Well, because of the negative charge of both reactants. Great. And now we have to go into the last catalyst, which is the autocatalysis. This is a term used to describe a reaction which is speed up by a product which acts as a catalyst for the reaction. So here you need to be able to interpret a graph and plot it as well. It goes like this. With a concentration over time graph, we would see that we have a slow uncatalyzed reaction which become fast and catalyzed once the product is formed. Now, the example that you need to know about this is between manganate and oxalate. Remember, oxalate is the ethanedioate ion. And let's see the reactions for this autocatalysis. Now, the oxidation is the oxalate, so C2O4 2-, which is converted into carbon dioxide and loses 2 electrons. The reduction is the reaction of the manganate in an acidic solution. So here I'm writing the half equation. Feel free to take your time to write it and balance it using the usual rules that I teach you. So balancing water, balancing hydrogens, and balancing the charges with the electrons. But for sake of catalysis, now I'm just showing the reactions. Now, if we think about what happens here and the overall equation, is that we have a transfer of electrons, and it's a lot of electrons, yeah? Now, the catalyst is the manganese. The manganese is the catalyst. So as more manganese is formed, the reaction speeds up. This is similar to the role of the ion in the previous reaction, and this is how it works. So the manganese 2+ is catalyzing this conversion to form Mn3+. So our catalyst is manganese, and manganese is changing from 2+ to 3+. So to balance the equation, this is what we have. And then, how does this react with the oxalate? The manganese 3+ is what it's reacting with the oxalate to form our product. Notice that the manganese 2+, yeah, is acting as a catalyst because it's regenerated. Now, a very common question that comes up here is, how do we follow this reaction? Well, remember that the manganese has a nice, very pretty color, and it's pink, which means that we can follow this reaction using a colorimeter. Because, of course, we need to be able to plot this concentration time graph. Go in the classroom and try the exam questions uploaded to put into practice this catalyst from the spec to the exam tutorial.